The side of the cube is given to be 18 centimeter. It appears to be present at 8 centimeter, where refractive index is real depth divided by apparent depth, 50 hertz. So I have collected the data from the problem. Hello students, this is SD Sir again from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. In today's session, what is that we are solving? We will be solving Model Question Paper 8. Hope you have gone through the previous sessions, solved the numericals, and have come prepared for today's class. The first problem, students, from optics, an interesting one. A transparent cube. So we are talking about a transparent cube of side 18 centimeter contains an air bubble in it. There is a transparent cube, ice cube tara, whose side is 18 centimeter and it contains an air bubble in it. Therefore, if I picturize, I assume this is the transparent cube whose side is 18 centimeter. The side of the cube is given to be 18 centimeter. And somewhere here, I assume it contains an air bubble. Now, when viewed normally through one face, the bubble appears to be at 8 centimeter from that face. Appears, not really present at 8 centimeter. It appears to be present at 8 centimeter. So when you are viewing the air bubble from one face, it appears to be at a distance of 8 centimeters from that face, which means, now I assume this is the first face and this is the second face. So when I view the air bubble from the first face, it appears to be at a distance of 8 centimeter from that face. And very interestingly, when viewed normally through the opposite face, it appears to be at a distance of 4 centimeter. The air bubble from the opposite face The second phase, it appears to be at a distance of 4 centimeter. So from the opposite phase, which is the second phase, it appears to be at a distance of 4 centimeter. I have to find the actual distance of the bubble from the second phase. Opposite phase idiyala, second phase, and refractive index of the material of the cube. Now, we have to find the actual distance of the bubble from the second phase. So I assume x is the actual distance of the bubble from the second phase. Then what is its actual distance from the first phase? Very good. So this becomes 18 minus x. So the first part of the question is to calculate this x. Now, we know that refractive index is real depth divided by apparent depth. So I'm using this concept of refractive index, where refractive index is real depth divided by apparent depth. Now I constitute this for the first phase and the second phase. So for the first phase, now n equals, what is the real depth for the first phase? 18 minus x divided by 8. I call this equation 1. Similarly, applying for the second phase, so n equals x divided by 4, equation 2. Can I not equate 1 and 2? Left hand side is the same. Therefore, 18 minus x by 8 is x by 4. Therefore, x turns out to be 6 centimeter. So, actual distance of the bubble from the second phase is 6 centimeter. Now, I am also asked to calculate the refractive index of the material. Very simple. Substitute x in equation 2. So, substituting x in equation 2, n equals 6 by 4 or n equals 1.5. So this is the refractive index of the material. The next one, students. Again, a problem on capacitors. A parallel plate air capacitor with air between the plates consists of 2 plates, each of area 0.01 square meter, which is separated by a distance of 0.1 millimeter. The two plates are separated by a distance of 0.1 millimeter. It is charged to a potential of 50 volts. Calculate its capacitance, charge on it, and energy stored. So area of each plate is mentioned, so which is 0.01 square meter. Distance of separation is mentioned, 0.1 into 10 power minus 3 meter. And potential is mentioned, which is 50 volts. So first we will calculate the capacitance of the capacitor. So given capacitor is a parallel plate capacitor whose capacitance is epsilon naught A divided by D, because very clearly he says air capacitor, no dielectric medium, it is air medium. So C equals 8.854 into 10 power minus 12, 0.01, 0.1 into 10 power minus 3. Get up with your calculators. Simplification part is yours. So this turns out to be 885 picofarad. So the capacitance is calculated, which is 885 picofarad. Next, charge, which is C into V. Basic definition of capacitance, Q divided by V, or Q is C into V. So 885 pico is 10 power minus 12 into 50. So this turns out to be 0.044 microcoulomb. And finally, we are asked to calculate energy. So energy stored is half CV square, 885 into 10 power minus 12 into 50 square. So this is equal to 1.11 microjoules. So this is the energy stored in the capacitor. The next one. A uniform wire. There is a uniform wire of resistance 24 ohms. Uniform wire of resistance 24 ohms which is bent into three parts. The wire is bent into three parts in the ratio 3:2:1, so that it forms a triangle. So the wire is modified as an triangle. A cell of EMF 4 volts and internal resistance 2/3 ohm is connected across the lowest of the three resistances. Calculate the current in each branch of this circuit. Which means now my basic aim is to understand which is the lowest of the three resistances, and the hint being wire. Its actual resistance is 24 ohms. It is bent in the form of a triangle given this ratio. So X being the unknown resistance, so we have 3X plus 2X plus X, which is 24. Actual resistance is 24. Ratio is 3:2:1. So 3X plus 2X plus X. So 6X is 24. So X is equal to 4 ohms. Therefore, R1 equals 3 into 4, 12 ohms. R2 is 2 into 4, 8 ohms. R3 is 1 into 4, 4 ohms. So which means very clearly R3 is the lowest of the three resistances. So the cell is connected across it. Now the wire is modified as a triangle. So the given wire is modified as a triangle. So this should be R1, this should be R2, this should be R3, because the cell has to be connected across R3, which is the lowest. So this is where I connect the cell. EMF of the cell is 4 volt. Internal resistance is 2/3 ohms. So EMF is 4 volt. Internal resistance 2/3 ohm. Now dear children, if you observe, R1 and R2 are connected in series. So RS equals R1 plus R2, 12 plus 8, which is 20 ohms. So initially I have calculated RS, effective resistance between R1 and R2. Now, this RS is connected in parallel with R3. So 1 by RS is, RP is 1 by RS plus 1 by R3, or 1 by RP is 1 by 20 plus 1 by 4. And on simplification, that turns out to be, so RP is 10 divided by 3 ohm. So I have calculated the effective resistance of the combination. Now I will connect or calculate the main current flowing through the circuit. And we know the expression for main current. So this is RP plus small r. You need to know this relation, students. Only when the concept is in deep, you know the expressions, you can solve the problems. So this is E is 4 volts. This is 10 by 3 plus 2 by 3. So which is equal to 1 ampere. So I turns out to be 1 ampere. Now we will calculate the branch currents. So assume I1 is the current flowing here. We know branch current is equal to main current into resistance of other branch divided by the sum of resistances. So this part is an assignment for you all. So use this formula, calculate I1 and I2. Similar problem I worked in my previous sessions. You can use that as a reference. The next one. A coil has an inductance of 0.2 henries and resistance of 40 ohms. It is connected to an AC source of 220 volt, 50 hertz. I have to calculate the power dissipated in this circuit. So inductance is given, which is 0.2 Henry. Resistance is given, which is 40 ohms. VRMS is given, which is 220 volt, and frequency is 50 hertz. So I have collected the data from the problem. With this, first I will calculate the impedance, because we know power dissipated is VRMS, IRMS into cos phi. If I want cos phi, if I want IRMS, I need to calculate the impedance. So the first part, as we know, impedance is root R square plus XL whole square. Capacitor illa. This is LR circuit. Or Z equals root R square plus 2 pi F L whole square. And on substitution, impedance turns out to be 74.5 ohms. So the impedance of the circuit is 74.5 ohms. Now once impedance is known, we know IRMS is VRMS divided by Z. VRMS is 220, Z is 74.5. So this turns out to be nearly 2.9 ampere. So IRMS is also calculated. So the only thing I require now is cos phi, power factor. What is cos phi equal to? We know the relation cos phi is R divided by Z. R is 40. So cos phi is 40 divided by 74.5. So cos phi is equal to 0.537. 537. So finally, power dissipated is VRMS into IRMS into cos phi, and on substitution, this is nearly 349 watts. So this is the power dissipated. The next one. So students, the problem says the atomic weight of radium is 226 radium. It is observed 3.67 into 10 power 10 alpha particles are emitted per second from 1 gram of radium. I have to calculate the half-life of radium. This is purely an assignment for you all. I will give you the hint, do the substitutions. Now the activity of radium is given. So A is equal to 3.67 into 10 power 10 disintegrations per second. That is the activity of radium. First calculate the number of atoms in radium 226, which will be N. Number of atoms in radium 226. Now we know A equals lambda n. So from this, decay constant is A by n. Once you calculate lambda, half-life is nothing but 0.693 by lambda. So this is how we solve the problem. Hope you have understood this problem solved today. The next session, I will work out numericals on the next question paper. Until then, have a nice time. Thank you.